In the previous video clips, we presented the space of all the complex numbers. Here are some notation: real part, imaginary part, complex conjugate, modulus of a complex number. Then the identification of the space of all the complex numbers with the two-dimensional real space as norm spaces and also as metric spaces. We identify the complex number x plus yi with the vector x y, and the norm of the vector corresponds to the modulus, the distance between 2 points, the open disk, open set, the convergence of the sequence of complex numbers described here, Euler's formula. Then we presented some examples of complex functions, z cube 1 over z, exponential of z, cosine of z, sine of z. We extended the real space. The axis of the real numbers is a subset of the complex space, and we extended some usual functions outside the real axis in the complex plane by using these definitions. Then we extended the definition of the derivative of a function, exactly the same formula as in the case from school. We defined the complex derivative by using such a formula, and the possibility to divide by a non-null complex number. Then we characterize such functions by using the real analysis. A complex function of complex variable can be described by two functions of two real variables. In this way, u is the real part and v is the imaginary part. And a very important theorem, Cauchy-Riemann, such a function is complex differentiable at a point z0 if and only if these two real functions are differentiable and satisfy these relations, Cauchy-Riemann relations. And if these conditions are satisfied, then the derivative at a point can be computed in this way. By using this, we proved that the derivative of the complex exponential is itself exactly as in the case from school. The derivative of sine of z defined here is cosine of z. We extended some formulas from school. Now we shall present the complex line integral. Complex line integral. In the case from school, you can see that the integral on the real axis, the real axis is a subset of the complex plane, and in school you can see that functions defined on an interval ab, real functions, and you computed the integral from a up to b, f of x dx. Now we extended the usual function outside the real axis in the complex plane, and instead of integrating on only intervals on the real axis, now we'll integrate on some path in the complex plane. We describe such a path by using a parameterization alpha beta, a function gamma. Here is the point gamma of t. Gamma of t has the real component phi of t, psi of t the imaginary part. So gamma of t, gamma is a function defined on an interval alpha beta. We usually consider the path contained in an open set D, and gamma of t has a real part phi of t plus I psi of t. We consider such path continuous. We ask a gamma to be a continuous function. This happens if and only if both phi and psi are continuous functions. If you compute, for example, the derivative of gamma at a point t0, this will be a limit, the usual definition, t going to t0, gamma of t minus gamma of t0 over t minus t0. That is, if we substitute here, is limit for t going to t0, phi of t minus, I shall put firstly the real part, phi of t0 over t minus t0 plus I, gamma of t, we have here psi of t, limit, limit for t going to t0, psi of t minus psi of t0 over t minus t0. And you can see that we get phi prime at point t0 plus I psi prime at point t0. We consider in the definition of the complex line integral path of class C1. We say that gamma definition is a path of class C1 if gamma and its derivative are continuous. Then we extend the definition to paths which are composed from a path of class C1. For example, such a path is the following. Firstly, this, and then this. Here, the derivative of gamma is not continuous, has a discontinuity, but this the closed path presented here is composed from two paths of class C1. Now we present the definition. If f is a function defined on D, and we have such a path, let us assume f is a function, a complex function, and we assume f is continuous. and the gamma of class C1. Then we define the integral of f of z dz along gamma, by definition, is integral on this interval alpha to beta f of gamma of t times gamma prime of t dt. This integral is, here we have an integral on a finite interval. F is continuous, gamma prime continuous. We have here a continuous function, so this integral exists. This is the definition. Let us firstly describe some important paths. We consider the circular path, the linear path connecting to points, and let us describe such a particular path, and to compute some integrals along them. Firstly, as an example, let us consider a circular path. Let us consider the unit circle in the complex plane. And we can describe it in several ways, but let us use as a parameter this angle t, which goes from 0 up to pi, and gamma. Here is the point gamma of t. This the unit circle, the radius is 1, and the real part from this right triangle, you know, here is cosine of t, and here is sine of t. So gamma of t is cosine of t plus I sine of t. You know that this is exactly exponential of it. So our path gamma of t is exponential it. It describes it a parameterization of the unit circle starting from this point. Now, if we want to describe a path, a similar path but of radius r, here is r minus r. So we can describe it in a similar way. We can use again as parameter this angle t, 0 to pi, and in this case gamma of t will be radius, in this case is r. So we'll have here r cosine of t, r sine of t, so we get r exponential of it. If the considered circle is a circular path, let us consider again the starting point. Here is z0, radius r, so here will be the point z0 plus r, describe the sense on the path. Again, we use 0. And this is just this circular path, but translated with z0. So in this case, gamma of t, in order to describe this path, is a translation of this one, is z0 plus r exponential it. We can also consider just a segment of such a circular path by choosing, for example, 0 pi. We can also modify the starting point on such a path. Let us compute an integral by using this unit circle, and as an exercise, compute the integral along this path of the function 1 over z dz. This is an exercise where gamma is this path. Solution. This our integral I. This by using the definition, instead of alpha and beta, we have integral from 0 to pi. We have f of gamma of t. In our case, f of z is 1 over z. So let us write f of gamma of t times gamma prime of t dt. And now we have to substitute integral from 0 to f of gamma of t is 1 over gamma of t times gamma prime of t dt equals integral 0 to pi 1 over gamma of t. Gamma of t is here, exponential it, times the derivative of this with respect to t is I exponential it dt. We can simplify here, and we get 2 pi I. So we have computed an integral along such a circular path. Another important path is a line path connecting two given points. For example, let us consider here 2 points, z0, z1, and we want to describe this linear path connecting the 2 points. A possibility is to use, for example, the interval 0, 1, and gamma of t to be 1 minus t times the starting point z0 plus t times the ending point z1. You can see that gamma of 0, when t is 0 is z0, gamma of 1 is z1. This is a linear path connecting two points. Let us, as an exercise, try to compute integral along gamma, the function to be z bar dz, where gamma to be the path from this picture. Here is minus 1 I in this direction. The integral we define here does not depend on the parameterization we use for gamma. A proof, you can find a proof, for example, in my book. The independence of the parameterization we use. We can choose here a different interval, and by a change of parameter to obtain another description. The solution, in this case, a description of this will be, if we choose here the interval 0, 1, then we can describe this gamma of t to be gamma of t 1 minus t, the starting point is minus 1, plus ti, the end point, and then we have to use this definition, a computation by using the definition. Integral along gamma z bar dz will be, we have f of gamma of t. So instead of z, we have to put this expression, integral from 0 up to 1. This is t minus 1 plus ti and we have to multiply by the derivative with respect to t is 1 plus I hope everything is okay here. Dt, this is a constant, so 1 plus I multiplied by integral. Here a primitive is t squared over 2 minus t plus t squared over 2I, and we have to consider this from 0 up to 1, and so now you know, let us see that this is a generalization of the integral you know from school. If our path of integration is a linear path, but it is this path from A up to B, this is the path of integration. And we have a function defined here, a real function, for example. And in this case, in order to describe this path, the simplest choice is to use exactly the same interval AB. And the gamma of t is just t plus 0I, t, gamma of t. And in this case, integral along gamma f of z, but instead in this case z is on the real axis, so z is of the form x plus 0I, so we can put here instead of z f of x dx, and if we use our definition, this will be integral from a up to b. F gamma of t is just t, so here it remains f. We can put here t, denote in a different way, times gamma prime is 1 dt. So this is we obtained in this particular case with this definition the integral you know from school, which is a particular case when the path of integration is a segment along the real axis. Now from school you know that for the computation of the integral, a possibility is to look for a primitive, an antiderivative. This method can be used also in the case of the complex integral. A definition, we say that a function g from b to c is a primitive of antiderivative of f from b to c if the derivative of g of z is f of z for any z. Okay, and now we have the following theorem. Let now if the function f from D to C is if G is a primitive of f from D to C, and gamma from an interval a b to b is a path in D of class C1. We consider only class of C1 or paths composed from such path. Then integral along gamma f of z dz is the value is g of gamma of b minus g of gamma of a. We have such a formula. Let us, here is set B, we have a function, a complex function, and here is our path described by using an interval AB. Gamma, here is the starting point, gamma of A, here is gamma of B. So if we have a primitive, here is f, also g is here, g, the derivative of g is f, is a primitive, then the value of the integral is the value of the primitive minus at the end point minus the value at the starting point. If gamma, remark, if gamma is a closed path in D and f admits a primitive in D, then the integral along gamma f of z dz will be closed path. The starting point is the same, and then this is evidently 0. If gamma, another important path, gamma is a constant path. A constant path is gamma of t equals z0, a fixed point for any t. In this case, you can see that integral of such a path of f of z dz will be 0 because the derivative of this constant path is 0. This factor is 0. We stop here now. Thank you.